In this series of experiments to follow, water and color dye are used to demonstrate the thermodynamic relationship between air and the built environment. By studying the airflow through a pavilion roof, a formal and scientific conclusion can be drawn about the performance of form on airflow. Designed to optimize wind flow through a structure located in the Caribbean heat, the roof plays a major role in sculpting the airflow around the construct. The process is to fill up a fish tank, adhere the models to a white plexiglass, dispense colored water on a plastic bottle into the feeder tube that feeds into the funnel, that once in the correct position can distribute water evenly across the system. After pumping water from the bottle, the colored water is released through the funnel and into the tank. The proposed site for the pavilion is in the Caribbean island of Cuba, which experiences the unique challenge of having to deal with thermal comfort through passive means only. It is hot and humid for most of the year, with prevailing winds coming from the northeast about 50% of the year. By orienting the pavilion in the same direction as the prevailing winds, we can create a continuing effect of sculpting the airflow to increase thermal comfort in the hottest months of the year. In the following series of experiments, I'd like to explore the effect of form on airflow with the specific aim of increasing air velocity and ultimately fresh airflow. In the initial test, the goal was to test an undulation of the roof to look at the effect of this form on airflow. We can observe the airflow sticking to the edge of the roof as it is guided through the model. This can be explained by the Coanda effect, which is the tendency of a fluid jet to stay attached to a convex surface. We can also observe a high pressure point versus a low pressure point in this model, which hints at the fact that air is prevented from moving into the system. On test number 2, the model is simplified and adjusted to avoid the extreme contrast of pressure buildup at the face of the intervention and encourage air through a sharp angle. One key observation in test number 2 was the Venturi effect. In viscid fluid dynamics, an incompressible fluid's velocity must increase as it passes through a construction in accord with the principle of mass continuity, while its static pressure must decrease in accord with the principle of conservation of mechanical energy. Thus, any gain in kinetic energy a fluid may attain by its increased velocity through a construction is balanced by a drop in the pressure. In test number 3, we can observe how a reflection of the roof plane creates a pocket that does not aid airflow. It could potentially even retain heat and decrease thermal comfort. In test number 4, an opening is added to the center of the roof plane to increase the amount of fresh air that enters the system. This air comes into the system before inevitably being redirected through the roof plane. In test number 5, we can observe a continuation of the Venturi effect as well as a horizontal progression from one module to the next. This is a successful model in that it hints at the possibility of horizontally stacking multiple spaces to create a continuing Venturi effect. Some of the limitations of the model in the experiments include things like the size of the tank, which limits the number of models that can be tested at once. It was also observed that flow slows down significantly as it passes through the models, which could be due to the nature of the mechanism through which the wind is dispensed, which relies on multiple distance bumps of the die. Opening locations could be tested at different positions through the roof and create different results. Also, the angle of attack could be studied by testing the head end of the roof at different measured angles. Overall, the success of the models hint at the possibility of using form as a means to impact thermal comfort in hot climates by creating a continuing horizontal stack of airflow.